All right, thanks a lot. It's a pleasure to be here. And I'm gonna start talking, and maybe something else we'll put on the screen. So I'm going to talk about global warming and extreme climate events, and mostly from the physical perspective. And there was a National Academy report on this topic that came out earlier this year, so I would direct you to that. I'm going to try to mix giving some overview about global warming and climate change with some examples of recent research from my group. And after the first session this morning, I was tempted to remove all the figures I have with p-values on them. But I decided I'm going to stand up here and take it. So you'll know when that happens. All right, so global warming. Why do we call it global warming? Because the global mean temperature is increasing. So we call it global warming. So don't be shy about calling it global warming. Some people have gotten shy, but it's exactly what's happening. It's just an observation. We've had about a degree Celsius of global warming over the last century. 2014 was the warmest year on record until 2015 happened. 2015 obliterated that record. 2016 is virtually certain to obliterate 2016 once 2016 finally ends. So we're definitely in an environment in which the climate system has more energy going into it, and that's affecting the global temperature, very clearly detected. It's also affecting many other aspects of the climate system, and this is why we call it climate change. Right? It's not just that the global mean temperature is changing, and I don't expect you to decipher all of the items on this list. The point is that it's a long list. We have mountains of evidence, thousands of papers detecting statistically significant changes, low p-value, changes in various aspects of the climate system. Temperature, precipitation, sea level, snow and ice, et cetera. So why is this happening? And to give just this super brief reminder, greenhouse gas concentrations have been increasing, in particular carbon dioxide, but also other important greenhouse gases. We know from the chemical signature of the carbon in the atmosphere that this increase in carbon dioxide concentration is due primarily to the burning of fossil fuels, as well as some contribution from historical land use change, deforestation. And we're now up over 400 parts per million. You might have seen some news articles about that in September. So even though there are wiggles within the annual cycle and from year to year, it appears now that we'll be solidly above 400 parts per million CO2 for the foreseeable future. About half of the carbon that humans have emitted has stayed in the atmosphere. About a quarter has been taken up by the land biosphere, and about a quarter has gone into the ocean. And you sometimes will hear of the other CO2 problem, the other carbon dioxide problem, which is ocean acidification. So we know, again, from historical measurements that the partial pressure of CO2 in the surface ocean is increasing along with the atmospheric concentration, and that is lowering the pH. And you should feel invited to call this ocean acidification because that's what's happening, right? So just like global warming, this is another observation, and it's in addition to the changes in the climate system that I had on the last slide. This is another big impact of the carbon dioxide that we are emitting to the atmosphere. So we know that the climate system is changing. We know that we're changing the atmospheric constituents in a way that we would expect to alter the energy balance of the planet. So how do we test cause and effect? How do we know what's causing the global warming and climate change? And this is something that we can partially observe, but we can't run experiments, right? And it's like I tell my undergrad students, like in science, we run experiments, we do controlled experiments. You put, when you're in 5th grade, you grow half the corn plants in the window, and you grow half the corn plants in the closet, and you give them the same soil and the same water, and you're testing the effect of light. I took it a step further in 8th grade, and I microwaved half of them, and I was able to conclude conclusively that microwaving corn plants kills corn plants. Unfortunately, we can't do that with the climate system, so what we do is we run climate models to run the experiments we'd like to run in the real world. And the key point that I want to make here is that for all the shortcomings, and my group spends a lot of its time trying to figure out the shortcomings, these are fundamentally based on the laws of physics. So there are some aspects that are essentially statistical relationships, but the real core of these climate models, literally the dynamical core of these climate models, is solving the equations of emotion. The equations of emotion. The equations of motion on a rotating sphere, ideal gas law, et cetera. Right? So this is just, I want to be clear, these are not like regressions between the concentration of CO2 and temperature. Right? That's not that kind of model. These are physically based process models. And so what we do is we run the corn plant experiment, but we run it using these climate models. And on the right are some results for global temperature from the IPCC. And you can think of the blue is like the control experiment. So this is, the models are only given the historical, the natural non-human forcings that occurred over the historical period. So these can be like the plants grown in the sunlight in the window. And then the pink is exactly those same climate models, nothing different in the code, but as a boundary condition, they're prescribed not only the solar variability and the volcanic activity, but also the real change in greenhouse gas concentrations and aerosols that actually happened over the historical period. So they're getting put in the microwave. Again, exactly the same climate models, very different outcome, right, with and without the human forcing. And it's, there's a lot of, there's much more to the attribution work that gets analyzed in addition to just global temperature, but here's what it looks like for global warming. This is the basis by which the IPCC concludes that it's very likely that the historical global warming is primarily caused by human emission of greenhouse gases and other constituents of the atmosphere. So if we have a change in the mean, this global warming, what does that mean for extreme events? And in the simplest conception, if you have some previous climate, which is the dark purple here, and you shift the mean, in this case to the right, and that gives you some new climate, or just a shift in the mean, no change in the shape of this distribution, then just by shifting the mean, that's going to change the area under the curve past some extreme threshold, right? So like say the 95th percentile temperature event, when that mean is shifted, that threshold is going to be crossed much more often, so that's more hot weather here in this cartoon. And what was the tail of the previous distribution also is going to be exceeded much more frequently, and that's more record hot weather, right? So the basic conceptual model, if we're warming the mean, we would expect just from this sort of first principle thought experiment, we would expect a change in the extremes. And so that brings us to this question of individual extreme events and whether or not we can scientifically test whether or not individual events like the extreme heat wave that happened in India earlier this year or the ongoing California drought, whether or not these events are influenced by global warming. And the title of this topic could be reframed as the question that many of us who work on this are now receiving from the public and the media and decision makers, which is essentially, is whatever's happening to me right now caused by global warming? And that's been occupying a lot of my group's attention over the last few years, given in particular the California drought, but other extremes as well. And it was a pressing enough question that the National Academy had a report on it, as I mentioned. So the answers that you'll hear to this question have evolved. I started my PhD in fall of 2000. So back then, you'd get some version of, well, you're talking about weather and we're talking about climate, or, you know, no, we could never do that because that's weather and we're studying climate, right? That was what you would see in the public from scientists back when I was starting my PhD. And there's been a real explosion of research over the last 15 years trying to figure out ways to ask this question. And I would say that most of that research is really trying to develop ways of framing hypotheses and testing hypotheses. There are some extreme perspectives that you will see in the public. So, anything from, we've had a degree of global warming, so everything is influenced by it, and that needs to be our null. And then on the other hand, we've had a degree of global warming, so if it's a 10-degree heat wave, then clearly most of it was not due to global warming. My view is that neither of these is particularly helpful from a practical perspective for a decision maker that's actually trying to decide how to plan California's water future. And I'm not sure that either is actually scientifically tractable. And so what we're trying to do is basically use a risk-based framing where the risk is a function of the physical hazard, the heat wave, the thunderstorm, the drought, but also how that hazard intersects with exposure and vulnerability, right? So if there's no one living where the tornado touches down, the risk is very different than if the tornado touches down in Moore, Oklahoma. So really it's this whole risk profile that matters, and what we can do, I think, for asking this question of individual extreme events is we can look at the probability of the hazard. And that's what I'll talk about today for the rest of the talk. So this is a bit of a challenge, and I don't want to go through this whole figure, but the point here is just that when we look at the historical record, we have a lot of variability for different kinds of extremes. There's a lot of variation in how well developed the historical record is. So there are some records like temperature records where we have a very well developed historical record, and we also have a really clear theoretical prediction for what should happen to temperature as a result of global warming. And then we have other kinds of events like tornadoes and severe thunderstorms where we have a very poorly developed historical record, and that creates challenge. So I think that's the first thing to consider, is that not all extreme events are created equal in terms of our ability to ask these questions. So given that landscape, what my group has done is we've tried to really focus on understanding the physical causes of any individual event, and then try to use formal and hopefully objective uncertainty quantification and hypothesis testing to both quantify the probability of those conditions in the world right now, given the historical record, and then also try to likewise frame hypotheses about the effect of global warming that we can test objectively and provide probabilistic statements. So I'll try to quickly run you through one example here of the ongoing California drought. It's not the recent California drought. It's still going. This has been a very both extreme and severe event in California. So how many of you are from California? All right, so we have a few who have been living through it. So this has been a record-setting event in the historical record in many ways: temperature, precipitation, snow, drought conditions, and it's also had a lot of impact. And I think that at the state level, this has been an event where our state decision makers have really worked hard to engage with the scholarly community and incorporate a lot of ongoing research in real time. And that's been a great example. And the event obviously has been a big event. California is a big part of our economy, et cetera. And it's even, we're seeing at the federal level or the potential federal level, really people even questioning whether there is a drought at all. And that's a very different landscape for scientists to work in than I think our California landscape, where it's been a very a real shining example of scientific engagement with the real-time decision-making process. So what did we find? So I'll show a few results from a paper in the Proceedings of the National Academy of Sciences last year. And we had a pretty ugly, convoluted figure in the paper, and the San Francisco Chronicle made a much more aesthetically pleasing and easy to understand version of it. And I don't know if you've had any of your scientific work end up going through the graphic design process and coming out the other side. It's pretty illuminating. The one word of caution I would note is if you do go through this process, just make sure that they don't remove the vertical axes, because that can make it hard to know what you're looking at. But otherwise, it's beautiful. So the main point here is that there hasn't been any long-term trend in California's precipitation in terms of the annual scale long-term mean precipitation. There's been a very clear warming that's pretty similar to the global scale warming. And there's been an increase in the fraction of years that have severe drought conditions. And so I'll walk you through what's going on. It actually turns out to be pretty simple in the end. And basically just counting up years. So if we look at the whole 120-year record of California's instrumental climate history, what you see is that we don't get any drought years that don't have low precipitation. It definitely takes low precipitation, about at least a half a standard deviation below the mean, to get a drought year. So that's a precondition for sure. But if we look at the whole record, about half of those, half of the years with negative precipitation, half of those dry years have been warm over California's history, and half of those have been cool, right? So we get about a quarter of the years that are warm and dry, and about a quarter of the years that are cool and dry. And it makes a big difference for whether or not that low precipitation turns into drought, right? What the temperature is makes a big difference. And it's about a low precipitation year that is also warm has more than twice the odds of turning into a drought than a low precipitation year that's cool. And what's happened over the recent decades as a result of this long-term warming is that California has achieved a kind of like a Lake Wobegon style state where essentially all the years are above average, right? So we're in the last 2 decades, 80% of the years have been warmer than the long-term average. We're on the cusp of really approaching 100% above the long-term average. And what that means is that even though there's no change in the probability of low precipitation, the probability that when low precipitation occurs that conditions are also warm has increased a lot, right? So if we compare the most recent 20 years to the previous century, the odds of that low precipitation is also warm have doubled. The odds that low precipitation turns into drought have doubled. And the fraction of years that are drought years has doubled. So that's our detection. It's clear that the conditions that create drought in California are becoming more common, not because of changes in precipitation, but because of changes in temperature. We can again ask why, going back to the climate model. So we just redo this same analysis that I showed you for global temperature, but we just do it for California. And what we see, and here are the p-values, what we see is that, in fact, the warming of California does occur with human emission of greenhouse gases. It's considerably less likely to occur without the emission of greenhouse gases. And we have very low p-values on the difference between these two populations. as you might expect, if California is warming, that changes the odds that low precipitation years are also warm. So again, we find, as with the observations, that because of that warming, with the full historical forcing, the human forcing, we find that the odds of low precipitation years also being warm have increased as opposed to not increasing without the human emission of greenhouse gases. Again, very low p-values, so high statistical confidence that these are different. So that is the story with temperature and precipitation and drought. Most of the change in drought risk in California has occurred because of the long-term warming of California, which has been, we're highly confident, has been driven by global warming. Now, the precipitation is interesting. We've had a super low precipitation, so I'll just take a minute or two to talk briefly about precipitation, because there's this famous ridge. Who's heard of the ridiculously resilient ridge? Few people, one person. All right, well, as ridges go, it's a famous ridge. So conditional on you knowing about ridges, you would have heard of this one. So essentially what happens is in California, we get our precipitation from storms across the Pacific. And when these periods of high pressure occur, that stabilizes the atmosphere sort of upstream of California and steers storms poleward. I sat outside at lunch today, and there was a ridge over Irvine during lunch, right? I mean, basically, the reason it's warm and sunny here most of the winter is because this is a pretty persistent condition. What's happened during this drought is that it's been very persistent, ridiculously resilient, some would say. So it turns out that this is actually not a static feature. It's not like a giant boulder sitting in the atmosphere. It's actually quite dynamic. But what's been unique about this drought is that we've had this blocking condition present for much more frequently during this drought than at other times in history. And in fact, you can see that all these areas of white here in the bottom right are areas where, in this case, the calendar year 2013 pressure was unprecedented in the last 50 years. So the highest geopotential heights of the last 50 years, and that coincided with the lowest calendar year precipitation in California's history, which you see in the red. So the first question we could ask is, have the odds of this changed? Has the frequency of this changed? In particular, has the frequency of this extreme pressure gradient that is really what drives the atmospheric circulation, has that changed? And the short answer is yes, according to our p-values. So we have, if we compare the frequency of extreme ridging in the early part of the historical record, first half of the historical record on the x-axis, with the later part of the historical record on the y-axis, the region that is sort of upstream of California, the latitudes of California, we see about a doubling of the occurrence of extreme ridging years between the later period versus the earlier period. So that's just looking at the observational record, no climate models involved. We can also ask, and this kind of gets to the heart of the uncertainty analysis for this question of single event attribution, and it's where I'll close. We can also ask for that condition that occurred during the drought, in this case the 2013, all those areas of white that I showed you in that map. This falls way out in the tail of the observational record, and so it's actually just a question of how probable are these conditions to occur in the current climate is pretty hard to quantify, at least if you don't collaborate with professors of statistics. Once we collaborated with the professor of statistics, it got considerably more tractable. So we see a lot of events like this that are happening around the world, events that are falling way outside of our historical experience. And so this is one example of how we go about asking this question. So we first want to know what's the uncertainty in the return interval of an event of this magnitude. And so that's shown on the right. So we're 95% certain that it's more than 126 years. We're 50% certain that it's more than 421 years, right? So that's how you could imagine different thresholds that you would prefer. But the point is that at a minimum, it's a rare event in the current climate, and it could be an extremely rare event. We also would be interested in how has the probability changed. And here we go back to our climate model simulation. So this pre-industrial would be the blue climate model simulation, sort of, more or less. The blue climate model simulation you saw before, and the historical is the pink one. And we can compare that distribution of return intervals in the pre-industrial climate model simulation and the historical simulation, and then take all of the different combinations of return intervals and calculate all their ratios. And that's what you see in this CDF. So in the end, NPR will report that scientists found that it was very likely that the odds of the ridiculously resilient ridge have tripled, and that's coming from this CDF. So the point is it's rare in the current climate, but it was even more rare in a climate without humans. So that's one example of the kind of framing that we and other scientists are using to try to answer this question of how are the odds of the conditions that are creating events like the California drought, are they changing? And the last slide I want to show is a picture from when I was in 8th grade. And Andy Revkin posted this recently during the California drought. This was a picture from a cover article in Discover magazine that was published in 1988, written by Andy Revkin. And what it shows is California's current water water status, which is very dependent on snowpack. And a lot of water storage from snow in the winter, and then melting of that snow in the spring and summer, and our water system is built. We rely on this snowpack for about 30% of our water storage in California. And back in '88, this is the bottom, shows Peter Glick's prediction of California's water system in 2050, losing that snow water storage, having less storage available in our reservoirs because of the lack of snowpack, more flooding in the winter, less water storage, so more water scarcity in the summers. And the amazing thing is that even though I was in 8th grade when this came out, it's exactly what has come to pass. And if there was anything wrong about this, it's that Peter predicted this for 2050, and in fact, it's exactly what we're experiencing more and more frequently in California now, including during this drought. So with that, I will close and say sometimes predictions are made, and 30 years later they come true. So thanks.